All right, welcome to Unit 4 on probability, random variables, and probability distributions. In this video, we're going to be looking at topic 4.11, 4.11, parameters for a binomial random variable. Now remember, what are parameters? Pretty easy thing, but you need to know what they are. Parameters are the mean and the standard deviation of that random variable. All right, so let's practice a binomial scenario, because if you don't understand a binomial scenario, then you're certainly not going to be able to understand the mean and standard deviation, which are the parameters. So here's an example. A battery manufacturer creates a large number of batteries every day. The company unfortunately knows that 18% of batteries made are defective. If 5 batteries are picked at random, let D be how many of them are defective. First question is this binomial? Now remember, for a problem to be binomial, you must first be given a probability of success. So in this case, it's obviously a defective battery, but it's successful in the sense it's what I'm looking for. So the probability of finding a defective battery is 18%. You must also be given a set number of trials, which in this case, I'm told that I have 5 batteries. So this is shaping up to be a binomial problem because I have these two things. But then I got to check my 3 conditions. The first condition is that the probability of success must stay the same always. So it's not like if I find 3 defective batteries in a row, for whatever reason, that means that the next battery is less likely or more likely to be defective. Absolutely not. Second condition, and again, these conditions are in no particular order, but on each battery, it's either going to be defective or not. It's either defective or it's not. That's it. There's only 2 things that can happen, success or failure. The third condition is that the trials must be independent of themselves. So if I take 5 batteries and 3 of them end up being defective, that has no impact on what's going to happen with the next 5 or the next 5 or the next 5. Each trial is independent of the next. So as long as all 3 of those things are met and I'm given the probability of success and I'm given a set number of trials, then I'm ready for the binomial model. Now keep in mind that anytime you're given success, you automatically also know failure, which is the complement of success. So this means that 82% of batteries are not defective. So even though I'm calling that failure, it certainly sounds like a battery that works is a successful thing, it's a matter of what are you looking for. Since I'm looking for defective batteries, then that's what I'm calling success. So they want me to create a probability distribution. Remember, probability distribution has all the outcomes. So of 5 batteries, 0, 1, 2, 3, 4, or all 5 of them could be defective. And I also need to calculate the probabilities of each of those outcomes. So let's go ahead and actually put all of our binomial rules together to find this probability distribution. So to find the probability that 0 are defective, that's going to be 5 batteries, choose 0 of them to be defective. That's 0.18 to the 0, no defective batteries, times 0.82 to the 5th, all of them are working, which is what I'm calling failure. And again, this first part right here is just going to tell me how many different ways that can happen. Then I could do 5, choose 1 defective battery. That's 1 defective battery times 0.82 to the 4th, 4 non-defective batteries, failures. I know that's a little bit weird, but you get the point. 5, choose 2, 0.18 squared, 2 defective batteries, 0.82 to the 3rd, 3 non-defective. 5, choose 3. That's 0.18 to the 3rd, 3 defective batteries, times 0.82 to the 2nd, 2 non-defective batteries. 5, choose 4, 0.18 to the 4th, 4 defective batteries, times 0.82 to the 1st, 1 non-defective battery. Finally, 5, choose 0, that's 0.18 to the 5th, all 5 are defective batteries, times 0.8 to the 0, none of them are not defective. Now remember, you could certainly use your calculator to calculate each of these. For example, how would I calculate the probability of 2 defective batteries? Well, I could do 5, choose 2, follow my directions of how I did that. Now remember, the notation is using the parentheses, but your calculator cannot work vertically. Your calculator only works horizontally. So this is how you input it into the calculator. But this is the 5, choose 2. And that tells me there's 10 different ways that can happen. So I take 10, multiply by 0.18, raised to the 2 defective batteries, times 0.82, raised to the 3. So there's 10 different ways that you could have 2 defectives, 3 non-defectives, and boom, there's your probability, 0.1786. All right, but now I got to repeat that for all of the outcomes. Or you may remember this. We can hit second vars, go to our list of distributions, grab the binomial PDF, type in the 5 trials, 5 batteries. Probability of a successful battery, which means it's defective, is 0.18. And then, for example, if I'm looking for 0, I'm looking for 0 defective batteries. Hit enter again, and we get 0.3707. So there's a 37.07% chance of no defective batteries. And then I could hit second enter, which re-brings that back up, change the 0 to a 1, and I'll get the probability of 1 defective battery, which is 0.4069. Now, if you're looking for one more way to make this easier for you, wait for this. You're going to love this. Now, the only thing with this is you don't get a ton of decimals, but you get a general sense of the idea. What we could actually do is we could go to y equals on our calculator, make sure any plots are turned off. And then under y1, check out what I'm going to do. I'm going to go second vars. I'm going to go and grab the binomial PDF. I'm going to tell it that there are 5 trials. Probability of success is 0.18, but I'm going to put an X here. Whoop, that's certainly not an X. I'm going to put an X here. So that means it's a function, right? So that means that how many defective batteries will vary. And when you're typing a function, you need there to be an X. Now, if you try to graph this, you're actually going to see nothing because remember, this is discrete. These are 6 distinct different situations. This is not going to be some curved graph because there's only 6 points and your calculator can't graph just those 6 points in this format. But what I can do is hit second graph, which is a table. Now check this out. All the probabilities are listed for it. So it literally creates a probability distribution for you. So the probability of 0 is 0.3707. 1, 2, 3, 4, 5, 6 are all filled in there. Now, notice the probability for 6 is 0 because you only have 5 batteries. So actually, if you scroll into the negatives, you can't have a negative amount of batteries. So that's obviously a probability of 0. If you scroll down to anything above 5, it's going to be a probability of 0 because you don't even have 6 batteries. How could you have 6 that are defective? So now you can fill this in. Now, again, like I said, you just got to be careful with, like, for example, 5 here. There is scientific notation there. So that would be 0.00019. So let's fill the rest of these in. So the probability of 3 is 0.0392. So this is, again, just a nice quick way to get the answers. Probability of 4 is 0.0043. And the probability of all defective batteries is very, very unlikely, 0.00019. And again, only 18% are defective, so if you would get 5 in a row that were all defective, that would be kind of weird. All right, guys, so that's how to make a probability model. But remember, that's not even what this video is about. This video is all about finding the mean and standard deviation, the parameters of the random variable. So let's do a quick recap on what the mean and standard deviation of a random variable are. If the random variable were to be repeated a large number of times, the mean of x is what we would expect the average to be per trial in the long run after many, many times. It's basically saying on average, the standard deviation is how much we expect x to vary from the mean. So this is our kind of our script, right? When we're talking about the mean and standard deviation of a random variable, we're basically saying is if that random variable were to be repeated many, many, many times, here's what we expect the average of those times to be and how much we expect that number to vary from the mean. That's the standard deviation. All right, so in our example, this would be if we were to look at 5 batteries a large number of times. On average, the standard deviation is how far the number of defective batteries will vary from the mean. So the big question now is, how do we find the mean? How do we find the standard deviation? Well, you actually have 3 ways. The first way is to use the formulas that we taught you for discrete random variables. Remember, a binomial random variable is a discrete random variable. So these formulas do work. To find the mean, take each outcome times its probability, add them all together. It's not too bad. The standard deviation is to take each outcome minus its mean, square it, times it by its probability, add all that together. The inside part is your variance, square root that variance to get to a standard deviation. But you know what? Most people are not going to use those formulas because they are very time consuming. So what a lot of people do is the second option is that they'll type everything into their calculator and bypass using the formulas. So they'll basically make a list in their calculator under stat edit of all the outcomes, 0, 1, 2, 3, 4, 5, and then they'll put the probabilities next to that in list 2, and then they'll run a one variable stats to get the mean and standard deviation. But when you got all these decimals, that kind of is a little bit longer as well. So I'm actually going to give you an even easier way. Now, this can only be used if you are binomial. If you are binomial, you have these two methods to find the mean and standard deviation that are much, much faster. The mean is simply n times p. That's it. Take n, times it by p. That actually makes a lot of sense. For example, if you have 5 batteries and you generally know that 18% of them are defective, you should just be able to take 5 times 0.18 and say that on average, there's going to be 0.9 defective batteries. So in the long run, you shouldn't even have one full defective battery. In the long run, you're going to average 0.9 defective batteries. Now, the standard deviation formula is also fairly easy, very simple to do. It is taking the square root of your sample size, 5, multiplied by the probability of success, 0.18, multiplied by the probability of failure, 0.82, which again we signifies 1 minus p. And we get 0.8591. So what this tells us that if we were to look at 5 batteries a large amount of times, on average we would expect 0.9 defective batteries. But the number of defective batteries in that sample of 5 will vary by 0.86 from the mean. These formulas are very quick and very easy to use. Highly recommend using them. You don't have to worry about using those long summation formulas. You don't have to worry about typing a whole bunch of stuff into the calculator. Just follow the formulas and they're very, very easy. All right, so that's really what the point of this video was, is finding the parameters of a binomial model. There's the mean, there's a standard deviation. Use these formulas, but please, you can only use them if you truly are binomial. All right, let's look at one more example. Let's kind of put everything together here and make sure you realize how easy this all is. All right, if we know that 7% of people have O negative blood type, in a large sample of 150 people, let's let X be the number of people with O negative blood. Now, first, I am not going to ask you to make a probability distribution. Can you imagine how big that would be? A, it is possible, so it is discrete, but it would be literally listing, well, 0 people could have type O negative blood. 1 person, 2, 3, 4, 5, 6, 7, 8, 9, 10, ... 145, 146 people, 147, 148, 149, or, oh my goodness, all 150 people could have type O negative blood. So when you have such a large sample size, it becomes very hard to make that probability distribution because there's so many outcomes. But again, that's not what I'm asking here. This question simply wants to know the mean and standard deviation. So if I were to look at a sample of 150 people, how many would I expect to have type O negative blood? Well, guys, follow the formula. N times P. It's that unbelievably easy. So 150 times 0.07 is 10.5 people with O negative blood. So in the long run, if I were to look at 150 people over and over and over again, I would expect an average of 10.5 people to have O negative blood. But that number could vary, so there is a standard deviation here as well. The standard deviation is found by the square root of 150 times success, 0.07, times failure, 0.93. So I get the square root of 150 times 0.07 times 0.93, and I get 3.12. So if I were to look at 150 people a large number of times, I'd expect an average of 10.5 of them to have O negative blood, but that number could vary by 3.12 from the mean. All right, one more extra special question. Same situation, 7% of people have type O negative blood, 150 people in a sample. X is how many could have O negative blood. Now, let's say the Red Cross actually held a blood drive and 150 people randomly gave blood. How few people would have to be O negative for you to consider the amount significantly low? Well, let's start off with understanding that we expect there to be 150 people times 0.07. So we expect 10.5 people to have type O blood. And the standard deviation that, again, we just calculated was 3.12. So there's actually two different ways you can figure this out. You could first say, listen, 10 is what I expect. Somewhere right around 10 is what I expect. So check this out. If I go to Binomial PDF and I say, all right, whoa, that's not what I wanted. I'm so sorry. Went way too far there. Second vars, Binomial PDF. I went a little too far. All right, here we go. 150 people. Probability that you have type O negative blood is 0.07. Now, what's the probability that there are 10 people? All right, well, let's go ahead and paste this in. Notice that this is very likely. About 13%, right? About 12.78%. This is very likely. Why is 10 people very likely? Because that's pretty close to the mean. That's what should happen. Now, obviously, if I hit second enter to get back, if I change this number to like 9 people, you have to delete the extra 0 there. So 9 people. Again, 9 people is only a little less than 10. So again, that's still fairly likely. I wouldn't say that if 9 people were O negative blood, that's significant. So again, I'm working my way down until I find something that I would guess consider significant. 8 people is 10%. Again, that's not that weird. It's pretty close to 10. 7 people, it's still, that's low, but 7% is not really significant. How about 6 people with type O? Well, okay, we're getting lower, but I don't even know if I would really consider that significant, right? And we could even go one more time here to 5 people. Okay, now, sorry, I hit it twice there. Now we're getting a little lower, right? So this is, excuse me, this is getting lower. Oh, but come on. I want to speed this process up, right? So remember what I taught you guys to do earlier. Go to y equals. Clear out what we had earlier. Second vars. Put Binomial PDF in your y equals. 150 people, probability of success 0.07. And remember, for x value, actually delete that and make it an x. Again, sorry, I did that again. There's x. Okay. So this is actually going to create a function because x is a variable. I don't know how many people are going to be. And then what I could do is once I bring this there, I could hit second graph to see a table. So again, now I could actually see it a little bit easier. The probability, let's scroll down a little bit. Let's just start again at 10. 10 is very likely, about 13%. 9 is pretty likely. 8's not surprising. 7, even 5 that we just saw, it's not that surprising. 4, I would say 3. The probability of 3 people is 0.004. To me, that would be pretty low. That would be significant. Personally, I reserve the word significant for anything under 1%. So I would say that if there were 3 people, I would think that that's significantly low. That is not very likely. Some people might say 4 because it's hovering around 1%. Okay, I can agree with that. But anything lower, look at the probability of 2, look at the probability of 1, look at the probability of 0. Those are very, very, very unlikely, definitely significant. But I would say somewhere right around 3 people is what I would classify as significant. So 3 people would kind of shock me. That's when I would start to wonder, wow, boy, there's supposed to be 10.5 people with type O negative blood. 3 is pretty low. How do I know that's low? Again, the probability is pretty low. But if you're actually looking for one more way to do this, now, I like what I just showed you, but if you're looking for one more way, think about standard deviations. We expect 10.5. If we go down 1 standard deviation, that would be 10.5 minus 3.12. We get 7.38. Going down 1 standard deviation is not really that weird. It's going down, but again, most data is within 1 standard deviation, so that's not really weird. Let's go down another standard deviation. 7.38 minus 3.12, and now we get 4.26. Now, I know these are decimals. That's just because I'm using decimals, but these represent people. So somewhere around 4. Okay, 2 standard deviations, that's where things do tend to start becoming kind of surprisingly low. So, like I said, an answer of 4 is actually not a terrible answer either, because if you go to our calculator here, the probability of 4 out of 150 people having type O negative blood is actually, a little bit over 1%. It's 1.2%. So that is, again, that's where we start to think, well, that's kind of weird. And then 3 is what would really shock me. If 3 people had type O negative blood, that would be definitely significant. I think that would be weird. And again, why am I saying that that's weird? Because it's supposed to be 10.5. That's how many people are supposed to have type O negative blood. And furthermore, the probability of 3, I just calculated using my calculator, is pretty unlikely. So again, I'm just trying to get you guys to start thinking about when does something become significant? And there you go. All right, guys. Hope this video made sense to you. And be ready to roll for the next one. Good luck.